So now we're going to discuss, you discussed so many ASR models. For example, you saw CTC based training, before that HMM based training, you saw RNN transducer based training, and I was always referring to the outputs as some tokens. So what those tokens can be, let's discuss that in a bit detail. It's very interesting, no maths, you can uh, keep away your notebooks and uh, if you want to write, yeah, you can still write. Okay, so here we are. We always saw these kind of models, and we said that output is k plus 1 dimensional, where k is the number of tokens and u is 1 is the last one is the empty token, or the which tells you to move t one step forward. In CTC also you saw k plus 1 tokens. The blank token was there and the remaining valid tokens. What are these units basically? So I'll start from the very uh, old paradigm, which is very intelligent paradigm because it was linguistically motivated. So when the initial ASR started, when I say initial, it means around the year 2012, when deep learning became very popular. Uh, um, when all these companies like Google, Amazon, um Apple, they were making their ASR models. What they were using as output is something called phonemes or phones, right? They use this term interchangeably, but they call it phones like in the literature, but technically I would say they are phonemes. Uh, or they use temporal states of phonemes. Let's say if you take a phoneme, you further model it with an HMM, which will have, let's say, 3 or 5 states. So basically, it is the phoneme. Now, let's see what is a phoneme and what is a phone. The difference comes from the studies of phonetics and phonology. There are two disciplines. One is called phonetics, one is called phonology. So, what is phonetics? Phonetics is concerned with the production and classification of words, speech sounds, right? Let's say you take uh, Punjabi. There is a phone there called, so in the phone in phonetics the units are called phones, like telephone, phone. So phones. One phone is, let's say, pa in Punjabi, let's say. Do you have pa in Hindi? Do you have pa in English? So these are phones. Hmm? Uh, there is a International Phonetic Association. They have some written notation. They want to write a symbol. They want to write every phone, like whatever number it is, hundreds or thousands of phones. They are trying to write them. Okay, the sound per should be written in this way, like per, and so typically you write a phone in this way. Let's say if sound per is there, you write the symbol, IPS symbol is per, and then you encapsulate with a telephone, right? Just to remember. So make two telephones around it, it becomes a phone. This is a phone notation for a phone. Whatever is written inside is a phone. And when you have multiple phones, you just put them together and then put telephone around it. This is the study called phonetics. Huh? And generally, all phones will have similar what? Let's talk in terms of spectra. Similar what? Frequencies, MFCCs. What will be similar in all phones? All phone means when I say per phone and anybody says that same phone, what will be similar? The position of spectral peaks? Position of spectral peaks? Yes or no? No. Pa, pa, right? Or they're not same. Peaks are moving. What is same? The spectral envelope, the shape of the envelope of the spectrum. So all phones will have same or similar spectral envelope. That's the rough understanding, huh? That's the study called phonetics. Then there is another branch which is called phonology. In phonology, we are not concerned with spectra or how things look, because things may look different, but they may be same. I'll give an example. Uh, Take example of k. You can say keep. So keep in British English, let's say keep, it's k sound. And then you have cart, k sound. Coot, it's it's sound. It's like k with hw, just to denote that it's not same as cart or keep. It's different. Coot, right? And seek, no her kind of sound. The her kind of sound is called aspiration. No aspiration. It's not it's k. Seek, different. The spectra is totally different. Phone is different. Scoop. So seek was like you are closing it. Seek, done. But scoop, it's again opening. Scoop. So all these are different phones, but they have the same phoneme k. It is all of these sounds are grouped together into the same phoneme k phoneme for English. So the phonology is language dependent, means the representations are language dependent. But yeah, phonology also has some things which are very, very language independent. And the phonology tries to do that. Like, how do you go from this language dependent groupings to something language independent groupings? The sound k behaves in a similar way in different languages. When I say behave, it means, uh, let's say you know Sandhi rules, huh? So the Sandhi rules are, it follows similar Sandhi rules across all languages. So that these are some details I will not discuss. But let's come back to the meaning of phonology. Phonology means uh, the way the sounds pattern in a language. Uh, so you can say phonetics is the surface form, or the realization or the recording which you make, and then you take spectrogram, you see the surface form. And phonology is the underlying representation of sounds, the underlying form. And phonemes are the building blocks of a spoken language. I'll give an example. Okay. Okay. So let's take this word, Krishna. What are the phonemes in this sound? How many phonemes are there? How many phonemes are there? Okay. So to help you, ka, ri, sha, ra, a. Five phonemes. Now look at the word kha se khargosh. How many phonemes are there? You can't speak a phoneme. You can't speak every phoneme. Let's say k. You can't say k because you have to add an in order to speak it. So, but ka halant, that's what we write it as. For khargosh, so it's kha ra ga o sh. Seven, right? In Sanskrit, it will be eight. There is no khargosh in Sanskrit, but if it were there, it would be kharagosha. Kharagosha, but it's not there. This word is not there in Sanskrit. But in Hindi, we generally omit the last khargosh. We stop at sha. So what about cat? How many phonemes are there? K, a, t. Cat. Three phonemes. Catch. How many phonemes? Huh? Three, four, five. Raise your hand. How many of you say three? How many of you say four? How many say five? Okay. So it is three. K, a, ch. Catch. Catch. Right? K, a, ch. So English can be tricky. So English writing system can be tricky. So Hindi is little relatively less tricky. Sanskrit is even lesser tricky. So that's how we see it. If you want more examples in English, unfortunately, I couldn't find any website which does it for Hindi. If you're interested, you can make one. I couldn't find any. For English, there are many, many. But it will be good to visit this website. and you can find phonemic representation for uh, whatever words you like. Now the question can be asked, yes, to construct phonemes, we are grouping together different phones to form phonemes. How do you find these groupings? What to group and what not to group? So the answer is minimal pairs. Minimal pairs tell you what to group, what not to group. Take any two phones. If you can find a minimal pair, what does that mean? If you can find two words with different meanings, which have all other phonemes same, or all other phones same, only these two phones are different. Let's say bad and pad. All phones are same in these two words. Only difference is b or per. The phone b and the phone per. Only they are different. We put them together and we say, do they mean different things in the language, in that particular language? Is the meaning of bad different from meaning of pad? Yes or no? Yes. Therefore, b and p are phonemes. That's why the phonemes are written with slanting slashes. Like you encapsulate them in slashes, not with telephones, but with slashes. That is phoneme. Phones are with telephones, phonemes are with slashes. All right. So b and p are phonemes. Okay. So two phones never occurring in the same context can be grouped together as the same phoneme, and two phones determined by minimal pairs are distinguished as different phonemes. Uh, let's say, uh, basically, that's how we define phonemes and phones. All right. So basically, if you can't find the same environment, then you can't find the, okay, you can group them together as phoneme. And the example is the sounds which I scoop, keep, peak, etc. Because then peak is always appearing at the end and cart is always in the beginning. So there is no reason why we can't, or it means they will never occur in the same environment. That's why you can group them together as single phoneme. Okay, now the phonemes, as I was mentioning, that phonemes have universal properties. So phonemes can be grouped as with different features, let's say coronal, dorsal, labial. So I will not go into the details of these properties or these features, but they are very useful and they have been used, for example, in Sanskrit Sandhi rules. And in English, although these rules may not be explicitly as formalized as we have in Sanskrit, but those rules are also followed. When uh, I was in Oxford, there was a place called Banbury, Banbury. How do you pronounce it? Banbury. Banbury, but nobody says it Banbury. They will say Banbury, Banbury. With the na becomes ma. So it is something. The same rule follows in Sanskrit also. The whenever you have a na and followed by some labial sound, it becomes ma. But the thing is, it's not formalized there in the way we do it here. But the same phonological principles explain that change and this change. So phonological features are very powerful in that sense. Okay, now this is some context which I want to, this will leave you with some thought that in English, you say pen versus pen, they are the same phoneme, per, because there is no pen in English. It's only pen. That's in British English. They don't say pen, they say pen. So, and pen does not exist. And so when you say the sound per, when you write per phoneme, it refers to per phone. But in Indian context, Hindi, pita and pita are different. So per and per are different phonemes. In British English, per and per are same phoneme. In Hindi or Sanskrit, per and per are different phonemes. So phonemes are very much language dependent, right? Some people say it's fita. It's not fita. It's pita in English or in Hindi. But because of English influence, they call it fur. But there is no fur sound in Sanskrit originally. Okay, so then you refer to the IPA. There is some very nice link on IPA notation here, and we have to stop. Actually, we started a little bit late, and I'm just left with some more slides, but let's do it in the next class then. But this is included in the mid-sem syllabus. Thank you very much. Okay, so far we saw phones, we saw phonemes, right? Now I will discuss another thing which is called syllables. You cannot pronounce a phone or a phoneme in isolation, right? So a syllable is the smallest unit you can utter. Generally, it's a nucleus of vowel surrounded by some consonants. Like if I ask you to say ka or car, you can say car or ka. But if I say no, ka is ka plus a, remove the a part, only say ka. You can't do that. There is no, this sound is not possible to, can be spoken. So what you do is, so syllables are the smallest units which can be spoken comfortably. So that's the meaning of syllables. Example, now this word is there, kamal or kamala. Let's say kamala in Sanskrit or kamal in Hindi. So let's take in Sanskrit, kamala, how many syllables are there? And what are those syllables? How many syllables and what are those? In Sanskrit, it's kamala. 3 syllables. Ka, ma, la. Each syllable has a vowel. Ka has a vowel and all have a vowel. So it's kamala. In Hindi, kamal, how many syllables? 2. Ka and mal. Ka and mal. Why mal? Because after la there is no a, you can't utter that. You just say mal. That's the second syllable. Okay. Acha. How many syllables? What are those? A and cha, or ach and cha. Okay, so there are 2 ach and cha, right? Because you can't say cha, that's difficult. But ach and cha, these are the 2 syllables here. Okay, what about sampada? 3. Okay, what are those? Yes, sam, pa, da. So 3, sam, pa, da. So generally you can see in in Hindi it's quite easy. Let's take some English words now. Let's take syllable. How many syllables are there in syllable? Confusing? How many syllables are there in syllable? What are those? Syllable. So there are 3 in syllable. How about spoken? 2. What are those? Spo and kan. So English, you have to little bit wrap your hand so that you can find out the number of vowels. Anybody knows what's the smallest, what is the longest word with single syllable? Single syllable longest word in English. How many syllables are there in speech? What are those? Spe and cha. There is no speecher. It's speech. How many? Only one, speech. And if I am not incorrect, the longest word is slightly bigger than speech. It's called screech. I think this is the longest word in terms of number of graphemes, which has only single nucleus, or sorry, single syllable. Screech. Okay. Anyways, you can verify. Maybe just ask Google, it will tell you. Okay, good. So now, our typical outputs could be syllables also. But how many syllables could be possible? Let's say in Hindi, if you say you have a single vowel and then surrounded by one consonant here or a blank here and one consonant here or blank here, could be multiple consonants also, like sometimes you may have multiple consonants also, no? So the examples so far we saw, they had only single consonants. Sampada also had sa, and ma, 3 phonemes made one syllable. So let's say typically if you take that, number of vowels into number of consonants into number of consonants, that will be the number of syllables you can get, right, in Hindi or, yeah. So number of syllables can be quite large. Okay, another output could be, forget about phones, forget about phonemes, forget about syllables. It could be simply the graphemes. Why graphemes? So graphemes are, what are graphemes? They are the units of orthography. That's how you write. For example, you write apple as A-P-P-L-E, and these are your graphemes, A-P-P-L-E. This is your orthography. Orthography means writing system. So language is not written, language is spoken. But writing is an approximation to that spoken language, right? And it misses many informations. For example, where are you going? Where are you going? Where are you going? Where are you going? All these are different sentences, but in writing it's the same, where are you going? So you miss so much of information in the writing system, and you try to compensate it as well as possible, putting question marks or something, but still you can't make it up. These are the things. So graphemes are quite an approximation of the actual spoken language, but okay. So, but the thing is, graphemes are easily available. If I ask you, tell me the phonemes for some words, for English, yeah, you can find from, there are people have manually made some dictionaries you can use. For example, how do you pronounce cat? So you will use that dictionary to say it's ka, a, ta. These are the phonemes. But for Hindi, it's difficult. At least in digital form, I don't know if any dictionary exists. Kamal, who will tell you that last la has no a? Or ladka, or what is sadak, last ka has no a. So, right? How do you know that? So in Hindi, it's difficult to get such dictionaries, and for other languages, it's even more difficult. I mean, other Indian languages. Huh? So basically, you may have written text in the grapheme form or orthography easily available, but getting corresponding phonetic transcriptions or phonemic transcriptions or syllabic transcriptions is very difficult. That's why if you want to scale up means you want to train with millions of hours of data or something of that sort, they have moved to graphemes. So the modern ASR systems, they don't work with, or they don't try to estimate phonemes or phones or syllables, but rather they try to directly estimate the graphemes. That's the reason. Just the scalability is the reason. There is no other linguistic reason to use graphemes, because we know that graphemes are very ambiguous, right? CAT cat, but CESS is cess. CATCH, so basically CH or CHECK becomes check. So the same C can be. So anyways, I think those examples will come here also. So in Hindi, what do we do? Whatever text is available to us, whatever decoding it has used, coding it has used. So there are many coding schemes for Hindi, like UTF-8 or something. So in my, let's say, computer, if I type Krishna, I will type Ka, Ra, I think Alt S, and then F for halant, and then capital N for na. But some other languages, some there are Hindi keyboards which can directly give you just type ka, ri, sh, and na, and a. So the different encodings people use for Hindi, and so depending on the coding, you have the sequence. Just that sequence is a grapheme for you. Okay, phonemes versus orthography. So orthography is the writing system, alphabets and spellings, for example. So there are examples where, as I told you also, that same phoneme can use different letters. So let's say in school, the phoneme is ka, school. How do you write it? Sometimes with ch. Right here, ch means ka. Right? Acne. The sound ka is represented with a C. Keep. The sound ka is represented with a K. Back. CK. Right? So same phoneme is represented with a different letter. Letter means the grapheme. Right? And it could be other way also. Same letter can represent different phonemes. Example is chorus, chick, niche. Same ch, but different sounds everywhere. In chorus it is ka, in chick it is ch, in niche it is sh. Different phonemes, but represented by same letter, ck or ch. Right? So these are some of the problems of working with orthography or graphemes. But still we do that. Still we work with graphemes. Why? Because of scalability. Linguistically, we should go with phonemes or syllables, but for scalability purpose, we stick to orthography. Okay. Then, let's come to the most modern technology. We don't even use graphemes directly. We use something called byte pair encoding. Now, when people saw, okay, there are graphemes like ABCD, ING, etc. There are certain graphemes which occur together very frequently. Let's say running, hissing, fishing, eating, right? So everywhere you have ING appearing frequently. So can we cluster it together? ING becomes one token, right? So what happens is number of tokens increases or decreases? Huh? In my vocabulary, the number of tokens increases or decreases? Increases, because I have added one more new token corresponding to ING. I is already there, na is already there, g is already there, but I have added a new token ING. So number of tokens in my vocabulary increases. But on the other hand, my accuracy of my ASR systems will increase. Why? Because whenever I hear the sound ing, I will not look for ING again. I will just take a single token, the ING token, and put it there. This byte pair encoding, basically, it increases the number of tokens in your vocabulary, but it leads to much better performance of your ASR systems. Right? In other words, you can also say your text length also decreases. Right? Earlier we were writing RUNNING, but if ING becomes one thing, then you're left with RUNN, and the whole ING is one token. So length of your sentence or word decreases by increasing vocabulary. So, but the performance improves. That is a major reason why people use byte pair encodings. So what is byte pair encoding? Let's look at this. So you start with the graphemes. Let's say I've taken this sequence deliberately because it's easy to show the concept here. It's not a genuine word, valid word, but it's easy to show the concept here. Let's say we have a string. Could be one word, could be multiple words, we don't care. There could be spaces in between. Every space is also a token or a grapheme. So just take all of them and just statistically treat them. How? You find now, so first of all you took the sequence of graphemes, then you make bigrams or pairs. CO is one pair, OU, I'm doing the wrong thing. Here, AA is one pair, AA is one pair, AB is next pair, BB is next pair, BA is next pair, like that. Right? And you count their frequencies. Whatever is the largest occurring or the most frequent pair, you make that a new token in your vocabulary. In this way, you keep applying it recursively or iteratively until you reach your upper limit of vocabulary. Let's say I want only, let's say here there are only 2 tokens to start with. I want to go up to 4 tokens. From 2, I want to go to 4. So then apply this once, get the highest occurring pair, and then change your, I will show you, okay. Let's say here, so which is the highest occurring pair? So 1 represents a sound, 1 represents, or 2 represent b sound. So 1 is a, or AA, this is AB, BB, and this is BA. And their frequencies are listed here. So AA is occurring 4 times. Can you see that? There is AA, again AA, here AA, and here AA, 4 times. So let's call AA as one single unit. So the most frequent pairs become a token. So in this case, AA becomes a token. Let's call it 3. Token number 3 is AA. Alright? And now rewrite the whole original sequence with this new token added. So when you see 1, 1, you made it 3. The next one is alone, so that remains 1. Then 2, 2 remains 2, 2 only. Then again 1, 1 becomes 3. Then at the end 1, 1 becomes 3. Clear? Is that clear? So this is how we... Now one thing you should take care of is that when you had 1, 1, 1, it became 3, 1. It didn't become 3, 3. That mistake don't do. Now repeat this process until you reach the maximum number of tokens you need. That's it. So example could be, so when you obtain this, let's say my vocabulary size is 4. How will now you reduce this one further? Make the pairs 3, 1, then 1, 2, then 2, 2, then 2, 3, and 3, 2. These are the pairs I found, and count their frequencies. I found there are 2 pairs which are occurring twice, 2, 2 and 2, 3. Pick any one of them and make a single token. So, and you will get this. So in this case, I made 2, 2 as a pair, 2, 2 as 4. So that's how. So now see, my vocabulary size has increased from 2 to 4, but the length of my output sequence has reduced from whatever it was before. How much was it? 4 and 11. 11 to 6. And corresponding ASR accuracy will improve. People use this byte pair encoding for ASR, for TTS, for machine translation, like for all kind of NLP tasks. People don't work with just the graphemes, but with byte pair. LLMs, large language models, they also use byte pair encoding. Right? Okay. Another advantage of byte pair encoding is that you don't need graphemes to start with. You can apply it on any string of, even a binary string or a string of bytes also. Right? For example, I say APPLE apple versus I say sa ek hi matra ba seb. Now the byte pairs which you get from apple and the byte pairs which you get from seb will be totally different, in different vocabulary altogether, and it becomes very much language dependent. So what people are doing, let's say when you want to make language agnostic models or not multilingual models. The same model can handle multiple languages. How do they do the encoding? They don't apply it on the characters or graphemes. They apply it on the byte representation of those characters. So every character will have some binary representation, right? Like what is it called, Unicode representation or something. You convert that into a binary representation, so you get a long stream of binary representation or a byte-wise representation. And then you apply byte pair encoding to those pairs. That's why the name comes byte pair encoding. It's not character pair encoding, but byte pair encoding. So you apply directly on the bytes. Then it becomes very, very statistical, and you are kind of ignoring all distinctions between languages. Just it's a sequence of bytes for you, right? Okay, yeah.